want to thank Rose for the kind introduction. Hello, everybody. I'm Birendra once again. First, I start my talk by thanking the organizers for bringing me here. I felt like just like a newborn baby after I listened to all the talks so far. I'm very grateful to previous speakers who has already introduced the subject very well. And so I will directly jump to the devices results. Actually, when I asked Sean how my presentation should look like, I said, focus more on graduate level, not very much for specialists. Nevertheless, so my title of the talk is Solution Processable Small Molecule Organic Solar Cells. Okay. So this work is done at CSIRO, Materials Science and Engineering. We could change our division name just today. Yesterday it was called Molecular and Health Technology, and today it got changed. So it's part of the team who did most of the work today. And this is the CSIRO team, about 50 people who focuses on the various types of organic electronic devices. And the work I'm going to present today is led by Kevin Winsenberg from the synthesis chemist point of view. And device plays most of the device data are collected by Scott Watkins and myself. And these are the funding organizations who funded our research. What's my talk motivation? So far I heard from, unlike, say, polymers, it's more like a spaghetti, you can imagine. So having a spaghetti-like materials, which is crystallizes at very high temperatures. Small molecules, unlike polymers, they crystallize at very low temperatures. So this was the point of discussion in the last minute. So by the nature, they crystallize at very low temperatures. So processing conditions are very different from that of the polymers. So that's how I'm going to discuss in the next 30 minutes. So apply these small molecules in organic solar cells. And we asked the question, why in the first place we chose small molecules? And we have a list, but don't take it very seriously. Polymers have several issues. It's difficult to produce the same batch of the polymers each time. It's a bit challenging still today. And we got chain end variations, polydispersity, and to remove the catalyst, for example, during the synthesis process is one of the challenging, and also very weak molecular packing. That will still have polymers, and still CSIRO is focusing on polymers. And if you remember one of the pioneering work of John Anthony on the soluble tips pentacene, for example, this molecule has done very well in transistors with very high mobility. And unfortunately, this very well-known material don't deliver very well in solar cells because they tend to interact heavily with the fullerenes, which is a very well-known acceptor. And so they form chemical reactions, and it's not very well suited for bulk reduction solar cells. So it has some luck on the bilayer-based devices. And very few work has been done on soluble small molecules, and I go very quickly from the chronological order. Again, this is the work of John Anthony on antradithylamine, then with PCBM, which delivered about 1% solar cells. And if you also remember the work of Klaus Blindholz with myrocyanin-based dyes, the delivery efficiency is close to 1.7 or even more higher in the recent papers of him. And also from Tobin Mark's group at Tobin Mark's group has also used this square end by semiconductors with C60 PCBM, has delivered about 1.2%. And very recently from the group of Queen's group in the University of California, Santa Barbara, has delivered pretty high solar cells efficiency with DPP functionalized oligodiophins. And they have even shown even higher ones, efficiency about 4.4, depending very much on the morphology. See the big difference from this to this shows that these materials are very finicky about how it processes the films. And borrowing the concept from the John Anthony's team at John Anthony's work, our team at CSIRO has introduced polycyclic aromatics by our chemist colleague Kevin Winsenbach. So these materials, I'll quickly go through without going into details, are synthesized with a very starting materials with very cheaply available commercial dyes and very straightforward synthesis process. You can get soluble derivatives of glycines. So you got a similar soluble derivative that's triacetylsilane substituted and makes it highly soluble. This is one example. So we got many of these derivatives, and I will show in a minute. One of the examples of these small molecules, you can grow single crystal simply because they crystallize very nicely. And if you do the single crystal axial diffraction, they tend to form a very one-dimensional kind of staking. So in finite one-dimensional staking with interlayer spacing about 3.4 angstroms. If you listen to talks or read the papers of John Anthony's nice review articles, they say that such molecules with typical one-dimensional stacks, they are not very well suited for high mobility organic field effect transistors. That's one of the motivations that we use this for use in organic solar cells. And so these molecules, if you do the electrochemistry, there's a very nice, I quickly go through, there's a very nice oxidation reduction peak, and it's not depending on the spin rate, scan rate. And this is one of the techniques that we have in CSIRO, measurement of HOMO-LUMO gap, very accurately using photoelectron spectroscopy in the air. Our colleague Scott Watkins does this very quick, it takes about a minute to do this spectroscopy in thin solid films. So these measurements are done in the solid state films. We can measure the HOMO level of the semiconductor. So this is as a result, P3ST as a reference, and these are our new crisis. And please remember that we have around 0.3 electron volts deeper HOMO levels with respect to P3ST, and this is going to be demonstrated in the organic solar cells. So these two different triacetylsilane substituted as well as test substituted lavender crisis has got HOMO is about 5.1 EV, and plus with combinations of optical absorptions we can get about LUMO is about 3 EV. So we got a band gap about 2 or a little more than 2 or 2.1 electron volt, and which we think that these materials can be used as a donor in solar cells with PCBM as an acceptor. But one of the very important things to do is also do small molecules. Yet when you do the simple laboratory experiments like to study this charge transfer between the two small molecules, and this is the optical absorption spectra. The green one is the pure diagonal glycines. Absorption onset is about 600 nanometers, corresponds to about 2 EV. And then there is sharp peaks of these glycines. And when we gradually increase the PCBM content, the absorption spectra becomes additive, so with a very weighted contribution of the individual component. One of the interesting things is you see when you gradually increase the PCBM concentrations, the peak position shifts in the lower wavelengths, so indicating that the lavender glycines matrix is heavily disturbed by the presence of PCBM, and so reduce the pi stacking. And when you do this luminescence, so it has a pretty nice luminescence at around 600 or more than 600 nanometers, and this luminescence is completely quenched by a small addition of PCBM. So showing a very good photoinduced electron transport, but also since it requires very few % of PCBM, it effectively quenches PCBM PL, which can be done with the minimum loss of the absorption coefficient of the blend. So this is one of the big advantages of having such a material, which we don't need very high concentration of PCBM to Apple devices. So we have seen pretty good, good band gap and good electron transfer. But one of the very important criteria about working with small molecules is that I've said in the beginning that small molecules tend to react with fullerenes. And this is one of the slides I want to show you. This is a well-known TIPS pentacene, and this is fullerenes. When you mix them and do the proton NMR studies in solution and study as a function of time, in the first half an hour, it started to react very fast, and these materials are not anymore useful for devices. And this is need to check for most of the small molecules of this type. And we have done these measurements on our crashings, and they seem to be stable with time. So, hence we put these devices, materials into devices. This is typical device geometry everybody is employing, and this is typical thickness about 75 to 200 nanometers. And here comes a very interesting point. Unlike polymers, these devices has to be processed in a very different fashion. I have shown 4 sets of device fabrication techniques for the device fabrication process, A, B, C, and D, with the corresponding airplane remains A, B, C, and D. And you see that device A is processed from high boiling point solvent at relatively low spin rate. And this resulted in a phase-separated films, largely phase-separated films, and overall device efficiency is very, very low, even at threshold of measurement conditions. And when we process these small molecules, unlike in the case of polymers, processed with a low boiling point solvent at relatively high spin rates, and then started to show rather smoother films and giving some kind of nano phase separated domains, and started giving some efficiency as high as 1.5% or 1.5%. And further increase the spin rate, like 8,500 RPMs, and the efficiency is increased to 2.25. So this is a very exact opposite phenomena, like unlike in polymers. So this result is reproduced for other molecules as well, with efficiency of 2.2%. So as we see that basically the same molecules with different spinning conditions and different morphologies give rise to different solar cell efficiency. We think that although the intrinsic mobility here is probably the same for all the films, but it's governed by charge carrier combinations probably in the devices. So we use these well-known techniques of photocell developed. So we have heard from previous speakers. I'm very grateful to them. And so to extract to say that a repeating of what people have said before, and this is a slide that I have taken from previous colleague Bill Della, where even if we have a very good optical absorption and very good band offsets, and all perfectly fine in the devices, but at the end of the day, it's a charge extraction which is limiting in the case, which is driven by in most of the cases, this is the drip length of the charge carriers, which is product of these 3 terms. And how do you measure these 3 terms? The charge carrier mobility and the lifetime of the charge carriers, and that's by using photocell. Almantas has given a very extensive talk on that. And I also just repeat, I think repetition was good. So this is the typical transient photocellic data, and from these one can measure lifetime mobility as a function of time, and carrier concentration as a function of time, and the lifetime of the charge carriers. And if you know, and if you have some signatures of suppose bimolecular combinations in your devices, you can use bimolecular formalisms and extract the bimolecular coefficient and bimolecular lifetime of the charge carriers. This is I'm going to show you in a minute. But before I go in blend of the films, I want to show you some of the studies we did here on pristine films. So these are the not the best photocell transients, but this is the pristine P-phase devices, and so photocurrent is a function of time. So this is the measurement under dark, and this measurement under light. And under the dark, there seems to be some kind of charge extractions. So this is some kind of dark the carriers present in the dark conditions in P3SD, where Yesterday, Gary Rumble has given a very extensive talk on it. So photocell extractions can give you some information of mobilities when in the dark conditions, which is pretty identical to the light conditions, mobilities as high as these numbers. And coming back to our dimensional crisis, we got efficiency of mobilities in the order of 1×10⁻³ square centimeter Wall seconds. And when it changed to other small molecules, so very similar, small molecule, but a different substituents here. Here is a 4-pentyl substituted instead of test substitution. And you see that big drastic change in mobility by a subtle change in the structure. So, which we don't know very well at the moment. We know the chemical, we know the crystal structure of these components here because we are able to grow single crystals, but it's still under debated how we can correlate this reduction in mobility from one structure of the molecule to the next structures. But if you now compare the bulk mobility measurements on the single components and that of the solar cell efficiency. So this there is upper three molecules have shown relatively higher mobility and relatively higher solar cell efficiency. In the lower three molecules have shown relatively lower mobility at the same time very poor solar cell performance. And actually I want to bring another conclusion to these results. If these molecules we found out that have a relatively higher solubility, it's about about 20 milligrams per ml or more, and below ones have shown solubility as high, a low solubility of 10 max per ml. So either the solubility affects the solar cells and mobility, or vice versa. So we have seen that solar cell efficiency is kind of correlating with the bulk mobility as of now. And here I come to the details because solar cell efficiency is anyhow governed by the bulk morphology and the bulk mobility of the blend, not the pure. So to do that, we bring in the mobility measurements of the blend. There's a TIPS diagonal crisis 1:1 blend with the PCBM in the solar, it's exactly like in the solar cells. So this is the typical photocell transient of current density functional time. And this is under the dark conditions, and one measures under light. This is the expression maxima around here, and gradually increase the electric field, and then the peak maxima shifts in the lower, shorter time scales. So from these three curves, one can extract the mobility, and this is the plot of mobility as a function of electric field. That's the electric field in the square root dependence of the, so we see a drop in the mobility when you increase the electric field. So that's one thing. One of the very important things we have seen is that mobility drops by 2 orders of magnitude in the place of blend. So crystal mobility is about 1.3, so 1.2 10⁻³. In the case of blend, we have mobilities in the order of say 10⁻⁵. So a drastic drop in mobility in the case of blend. And I won't go in detail, but we have used the X-ray diffraction and the synchrotron-based data to see that in presence of PCBM, the small molecules tend to have a reduced pi stickiness. So it had drastic reduction in the mobility and charge transfer properties. So this is one phenomenon, and of course I won't also go in detail, but the negative field dependent mobility where Attila has pioneered this works. If you have any questions, please ask Attila in more details. How much time I have?
You have 7 minutes.
Great, thank you. One of the, I want to go a little bit slow here, I think. In general, in the university laboratory experiments, if you have a solar cells and measure the solar cell efficiency using the AM1.5 light, and so people, in general, it's very quick and easy experiments. Measure the current, source of the current density as a function of power density, and measure this exponent alpha. Typically, if alpha is greater than 1, people attribute this to the dominant length type combination. And if alpha is in between 1 and 0.5, people say it's dominant bimolecular type combinations. Well, it is being said that this field-dependent mobility comes into the picture, and one has to do much more detailed study. But this, as I said, it's a very quick and easy explanation. In our small molecule blend solar cells, slope is about 0.95. So we think that it's more of a bimolecular type of combinations. So we analyze this data based on bimolecular type of combinations. And coming back to the photocell transient, current density is function of time. Now we play around with the delay between the voltage pulse and the light pulse, which cell delays about 0.8 to 60 microns, 6 microseconds, and you see the shortest delay gives you highest extraction of charge carriers. And now from this data, you can now extract the mobility as a function of time, and also you can integrate this area under this curve and divide it by the electronic charges. You give you the charge carrier density. And this is the plot on mobility as a function of time. See, the mobility is almost constant here as a function of time. It gives you so-called non-dispersive charge transport. This is very interesting for us. And if we plot the carrier density as a function of time, we try to kind of use the bimolecular combination equations and the fit experimental data using the theoretical fit. It fits pretty well in the first, say, about 10 to 20 microseconds. And from this we can extract the bimolecular combination coefficients in the order of 6.5, 10 minus 13 cubic centimeter per second. And the lifetime, again, it's, I won't go in detail, but lifetime is about 50 microseconds. And so we have seen much reduce in the solar cell, in the bulk mobility, that's electron hole mobility, and at the same time we have seen much reduced bimolecular combinations. Now, I will bring in very close the work of Almantas before when he was a graduate student. So, PCBM devices, which is one of the very classical materials we have in today's community, have shown relatively low carrier recombination coefficient, bimolecular recombination about 1.5 to minus 14, and very long lifetime discharge carriers. But at the same time, it has got a very high mobility in the order of 10 minus 4. But in the case of our small molecule blends, it has got a very low efficiency, or 1 order of magnitude lower mobility, and the bimolecular recombination is about 1 order of magnitude higher than the PCBM. So now, if you compare the mobility in the lifetime of the charge carriers of the two cases, in this case it's much more higher. The product lifetime and product is very high. So I think the efficiency here in this case is higher because we got larger, much longer drip length of the charge carriers in the case of PCBM. Nevertheless, it has seen very similar type of recombination dynamics. I'm going to come in a minute. But before that, I want to just take another opportunity to discuss about another way of explaining of measurement of field effect transistor mobility. I know there is a lot of debate on measurement of mobility using field effect transistors, but there are some valid points. When we discuss that, so transistors being 3 electrode devices, source, drain, and gate. Semiconductor is separated by the gate electrode by a dielectric. And when you apply a gate voltage, charges are introduced in the semiconductor very close to the interface dielectric. So this is a Birendra spin coated on the PCB on the surface modified silicon dioxide. You see these molecules crystallize very nicely and they form some kind of sugar cubes. And the crystal can be as large as 1 to 2 microns. Typical transistor behaviors, very well behaved. So square root dependent on the source of the current, drain current and function of gate voltage. And very nice transistor output characteristics. And now bring in a table of dibenzoic crises with different subsystems. And this is about whole mobility of all the 5 compounds. We have it. And now they compare with solar cell performance. Unfortunately, they don't correlate. Of course, they are expected to not to be that correlated. So all the mobilities are 10 minus 3 in these compounds. So and the solar cell efficiency is drastically different for each of the compounds. So we give a plausible explanation here. So organic field effect transistors, unlike in the bulk mobility measurements, the orientation of the molecules in the interface is very much driven by the surface chemistry of the dielectric. So molecules may be oriented in a certain directions which may not be very much mimicking what is happening in the bulk of the materials. This is one of the, and it's also the field effect transistors, it's that such a way that charge transport happening only in the interface of the semiconductor. But what happened in the case of blend? This is under debate. Probably in the case of pristine terms, you have nano domains which are molecules oriented in different and very unique directions. But in the case of blend, maybe you have certain conditions, like in the case of solar cells, where the orientation of the small molecule is disturbed by other small molecules. For example, this one here. So we took this advantage and measured the bipolar charge transport of fifth diagonal pricing and PCBM. So, and this is the Venn diagram. So this PCBM and diagonal pricings, and gold as a contact, and we still have big barrier height for electron injections. And even with this barrier height, one can observe very good electron transport and very good pole transport. And this is the output characteristics of the electron transport, because many people don't trust unless until you saw this curve in transistor community. So we saw this graph. And now compare the field effect transistor measure mobility and that of the bulk mobility measurement using photocell. So take this example of diagonal pricing 1. Neat films mobility is about 10 minus 3. Blend films 10 minus 5. Whole mobility, electron mobility is 10 minus 3, which is very valid. The FET need mobility is 0.02. And now compare with the bulk mobility measurements. So need is about 10 minus 3, and the blend is about 5 10 minus 5. And we think it's the whole mobility, because we are measuring one of the slowest components, which is quite comparable to the electron mobility and whole mobility of measured by FET and that of the bulk mobility. And so in the case of blends, simply there is a correlation between the bulk mobility measurements and the FET measurements. And we think that this is still very number in the case of bipolar transistors. Now coming back to the solar cells, as Amantis has given very nice introduction to the length-driven recombinations. In the case of solar cells with length-driven recombinations, it's supposed to be a diffusion process, not electric field driven. So this length-driven recombination is just a sum of the two mobilities times electric field divided by the dielectric constant. And if we take this value and measure the length-driven recombination coefficients, they're in the order of 6.1, 10 minus 8 square centimeter per cubic centimeter per second. And we remember the bimolecular recombination coefficient is in the order of 10 minus 13. So ratio of length-driven bimolecular recombination by length-driven recombination is in the order of 10 minus 5. This is huge numbers. Huge numbers are the measured values. So we have seen very reduced bimolecular recombinations in the case of two small molecule blend solar cells. And now if you recall some of the numbers from P3 PCBMs, the length-driven recombination is about 10 minus 10, and length-driven and bimolecular recombination is about 1 10 minus 14, and so the ratio is about 10 minus 4. So we've got pretty comparable reduced recombination with the two systems. So this leads to the another explanation that why we see such a reduced recombination in the case of two small molecule blends. And I have explained this in the first few slides that small molecules tend to crystallize very fast and they produce first phase separated films. And probably in this process, the carriers don't meet after they are generated in the films, and hence reduce the recombinations. And there are other imbalance mobility and charge carrier concentration gradient. The work of Ladin has been acknowledged. So in our small molecules, although mobility is relatively low, but because of the reduced charge carrier combinations, we think that that leads to the very high efficient solar cells. I come to the conclusion that it's very important in the case of small molecule solar cells that we need to have a very specific control of the morphology, which should keep the device performance. And the trick is that you have to use low boiling point solvent. And we have seen the lower mobility do not affect the SARS carrier extraction, SARS carriers or salts. We have observed this lower mobility, but it's not really affecting the solar cells. So what is important is the lifetime of the SARS carriers. And we have seen the reduced combinations in small molecule-based solar cells. And we think that dibenzoyl are one of the very attractive new class of small molecules that is introduced in this community, non-tyrosine-based solar cells. With this, thank you everyone for staying awake.
Yes. With your processing of your Queensland curve from digital boiling point from what distance did you see for your zero sample?
Question is, I'll repeat the questions. So for the small molecules with the low boiling point solvents processing, what is the condition of preparation for a cell sample?
Yeah, I'll see whether the film that you tested.
Yes, I forgot to mention that these films are the same films that are used to devise solar cells, so about 70 nanometers or slightly thicker films. They're not big difference from solar cells. So that's the reason we want to maintain the same film in the same area of the devices.
You had no problems to do the seal, you had no shorts?
No. Okay, although it might look to that morphology is very rough, look like, but they are only in the nanometers. So the film thickness is about 70 nanometers. So that's good enough for us to measure.
Did I understand you correctly that you said that the recombination is Langevin type, but reduced because the charge carriers are in a different domains?
Exactly.
And they don't
meet.
Yeah. Because one charge is fixed, or if they moving, so they will come to the interface.
Yeah, it's plausible explanation. One is there's already, you see that the SARS carrier mobility is different. The electron is higher and hole mobility is 10 times or 100 times lower. So they are moving at different velocity. Second thing is they are probably generated at a different position and then they'll meet it. And we still trying to find out what other possibles that such reduced recombinations. Very happy to observe it, but we don't know the answer yet.
Just on that, isn't another possible explanation for this nothing to do with morphology or anything, that the singlet excited state is of higher energy than the separated?
Yes, it's possible. It's possible. One of the things that I mentioned, I forgot to mention, is this: between the two small molecules, the dipolar energy levels, the interface dipoles, they might also play the roles like the barriers to recombine it, actually, after being separated.
I don't know if this is possible or whether it's all compatible, but have you thought about putting these two systems into a bilayer?
Oh, yes. We put it, I took up this because we just put the same device structures and do the evaporations of small molecules. And got really good solar cells, about similar. ITC is about 35%. And of course, there's a low mobility and high series resistance. But if you compare the bilayer and that of the molecular junction, pretty close. So that's one of the reasons I wanted to say that being small molecules, advantage you can evaporate these small molecules and form bilayer, and you can forget about the problems of recombination. The morphology issue. And you can test this material straight away, without having to go to the morphology issues. So, and yeah, one of the students is working very hard on this, and this is very preliminary results. We have a way to, we can improve further the efficiency.
Just a price talk on Saturday.
Surely.
I've seen this reduced recombination 10,000 times. That was in extremely high efficient PhDs, where the IPV, the maximum value of IPV is really low, like 95, 90%.
Yeah.
How is it in your cells?
Oh, we haven't measured the IKV actually. We haven't measured it.
That makes you later to check.
Yes, yeah, definitely. That's a good point. Yeah.
I expect we have no recombination at all.
Thanks for that. And I think it's a very good point. We have yet to measure it.
Yep.
Just to make sure, did you ever check what your domains really are? In other words, have you ever looked at residual fluorescence?
Not really. Not yet. That's all very.
Because many times we just take it for granted that one of the domains is one material and the other is the other. But that really doesn't have to be true, right?
Yes, definitely.
So,
Definitely. Yeah, that's another domain that very interesting to look into it. Yeah. Yeah, that's point for collaborations actually.
well, simple
Yes.
itself.
More questions? Okay, so I think what we want to do is get all four speakers.
Yeah, I think just
all four speakers. So
come up in front.
and then people can ask questions and